So what is private voting? Voting is one of the most important ways of ensuring that fair decisions are being made, and without voting, people would not be able to have say on certain decisions and propose change. So advantages of private voting, they're like anonymity, time efficiency, security, and more basically. And the voters themselves and their votes are anonymous, and uh, they are verifiable by anyone. So use cases. So there are many use cases like DAO voting, boardroom elections, community pools, and more. What we have achieved, so it is scalable because it doesn't depend on number of voters, and we also built a off-chain storage API, so it is ready to go, actually.
And about the user flow, so it's actually very similar. First of all, the election admin, so anyone on the chain, deploys a public key list of voters saying these keys will be able to vote. And in our system, we identify candidates as just numbers, but you can use any type of identifier, of course, username or any other public keys, etc. But for now, they're just indexes, so number of candidates is enough to create actually the actual candidates. Then it starts the contract and the vote process starts. Each voter should set her or his nullifier before voting. They can set their nullifier multiple times to protect anonymity. Of course, it's a randomly used value, and once they vote, it's no longer be used. So it's just to verify the voting process. So it's similar to Carol's structure. There's no time limit to set a nullifier, and there's like no time limit to use the nullifier because it's stored on chain. And once they have their nullifier, they can vote using their private key and their nullifier. And once the vote is over, the candidate tree is updated. The end of the vote is called by the election admin, of course. And once the candidate tree is updated, this is the first and final time the tree is updated, by the way. Anyone can verify that number of candidates, the vote on any number of candidates is correctly announced by the admin. There's a small problem with our code. It's not a problem actually because it works perfectly, and it's not synthetically so high time complex. But we should count each candidate separately right now. So like if there are 10 candidates, we should count the votes separately for 10 of them and actually get the results. But the candidate tree is not updated during this process. So you can like learn number of votes on every candidate as you like. It's not only the election admin, anyone can learn this. And they can verify that this is true with the candidate tree. And how it's anonymous, of course, it's because of random nullifiers. The other two is not that important. Since random nullifiers are chosen by voters, and as we said before, it's not important before the vote or after the vote, so they can choose what they like. And once they use it, their actual vote information is hashed using this nullifier. So no one can see if they voted or not. So they cannot know who voted a vote, and votes are not identified by voters. But if they try to vote again, they should give the same nullifier and same private key. So we can actually see that there's a voter on the tree with this voting information. So we can verify that voters voted only one time, but no one else can see if they voted or not without nullifier and the private key. And the Merkle tree, of course, we have a hash Merkle tree root on the chain, so you can verify if something is true, but you of course need an off-chain storage. We will go deep into that, but it's not really about the contract. And reducer logic, so it's actually about scalability reducer, but in great number of voters, it also gives some kind of anonymity, extra layer of security actually, because like with reducer, we are able to update the state of the chain at the same time. Like 2 votes can be voted at the same time on the same block. And thus, you can see that like 2 votes are given, but you cannot say which transaction sent that vote. Actually, even you can see that's still anonymous, but it gives a more chaotic anonymity. So it's, I don't know, it's a better site to look at. And to have a deeper look, we can see the code. Actually, I will share my screen. You can see the code too, right? When I change my screen. Okay, I'll take this as a yes. Okay, great. So I will start the test behind so that it works as we talk. So we have a contract basically. We have 2 models, voter and candidate model. Voter model is identified by the key. This is the public key of the voter. It's given by the election admin, as we said. The nullifier, it's default nullifier, 0 at first. Voters should change it to vote. And his vote information, of course, false at start, and once they vote is true. So our methods are as given. And for candidate, we have key. So this is the key of the candidate. Like they can be a number. In our system, it's an index on the tree, on the array actually. But you can use a username or anything of your choice. It's not that important what you choose. The vote count on the candidate. So this is important to actually see how many votes given to candidate. And witness. So this is the path of the candidate on the tree. We can recalculate the path using the key. It's possible, but it's easier to give with witness, and it's also more usable. Like if you want to have custom usernames for candidates, you can just change this field and appropriate functions, and then it will be working, ready to go. Add vote just adds one vote to the candidate and returns new candidate. So what's in our contract? We have, of course, the start method. Actually, once you deploy, everything is set to default values. You must actually start the election before the voting starts. So we give 2 routes. We don't check if these routes are correctly initialized or not. We just assume that they are, because if they are not, no one will be able to vote. You can, of course, have an extra layer of security, but it's not necessary. You can just do this in the front end, because as we said before, voters cannot vote if any of these routes are not correctly initialized. And they can check that if their information is on the route or not, because everyone can see on-chain values, and they can verify if it's given correctly, if it's initialized correctly or not. So no need to be checked by us. Once the vote is started, so we change the status to started, so vote is now ready to go. Each voter can call these 2 functions in order. First of all, they should set their nullifier with their private key, their old nullifier. This is the default nullifier at first, but they can change as many times as they like. And their nullifier, and of course their path on the Merkle. So they update their nullifiers. They can call this function as many times as they like. If they feel secure, they can call more than once, but one is enough. And once they change their nullifiers, they actually can vote. To vote, they just gives the candidate index, and of course their private key, nullifier, etc. All is private. So they vote, and once they vote, we don't update the candidate tree. This is the important part for scalability. We just dispatch an event on the reducer, so we can identify that the candidate is now voted. And there's 1 vote on this candidate, but the vote is not yet counted. And once the election is ended, we call the tally function. We call the reducer to count number of, and we update the candidate tree. We add vote for each action, and we calculate a new route. I go very fast, sorry, but we don't have enough time to talk about everything. And the count function is specific to each candidate. Maybe it's named poorly, I don't know, but each candidate. So you give the key of the candidate, and we count number of votes on this candidate. So we see if it equals the key. If it equals, we add 1 vote. So in the end, we return the vote count for that candidate. So we know that reducer is not actually on-chain storage. So you should not use this reducer as this. But this is actually a very easy problem. If you feel that you will have more than, like, I don't know, enough votes than reducer can handle, then you can just change this logic to call tally more than once, and you can update the candidate tree. But once you do this, you cannot call the count function many times. So you should be able to return number of votes on the candidates from the tally function. Right now, it's not like possible to send an array of results, but like if you know that you will have 10 candidates, then this tally function will just return 10 numbers, 10 fields. And so you can count these 10 fields, you can update, and you can return those 10 to store on off-chain because it will be verified by the chain, not stored. And you can just improve the conditions on the reducer, and you can just reread new events, new votes. So this is basically our contract. And about our tests, actually, I just will say that it all passes. So we test voters vote, they're all private. And in the end, we check if the vote count on candidates is true, and it is. So yes, it works.
So I will sum up with what can be done next. So our zkApp is ready to be deployed to Berkeley, but we will need an user interface for sure. And we can also work on some other voting settings. Like right now we have we keep the candidates as indexes on an array, and that's off-chain mapping. So we can turn it into an on-chain mapping. And also we can support like on one voter, multiple votes type of votings, and also quadratic voting. So that's pretty much all.
Yes, thank you for your time.
Yeah, so we have to mention also that's a proof of concept.
Yes.
There's still lots of things to do.
Yes, of course. So we can take questions.
Amazing job. Yeah, it's kind of interesting to see both approaches, Carol's team's approach and then your team's approach. Question from Vincenti.
Oh, I cannot see the chat if there's.
He says, are the votes counted by summing up events on the back end?
No, events, we call it events, but they aren't actually events. So there is this reducer logic on the Mina to allow multiple state updates at the same block. So if two voters try to update the same candidate at the same time, like they will try to increase number of votes on the same candidate, they will say that number of votes is X right now and I want it to be X plus 1. So one of the transactions will fail because they will both take initial condition as X, but one of them will complete first, and the initial condition will change. So in order to prevent this, Mina has reducer. So we dispatch new canton reducer. As we said before, this is only for scalability, not anything related to anonymity, because actually it's not possible to see if the voter has voted or not, as you cannot check if his vote information is on tree since it's hashed with the nullifier. But like even if you're able to see it, you can just see that new count is dispatched.
I guess I have a quick question. You said you guys haven't built the UI yet, or you guys already started building the UI?
Like we have started at first, but then we said that no, we don't have enough time. Let's go on the contract. So like we have the interaction functions and we have API, like so we are ready for the UI actually. So, but we are not sure about how to like create the UI too. So yeah.
Okay, cool. My question was just going to ask like how you're planning to, like what you're planning on using to build your UI, but it sounds like you haven't started yet, right?
No, we want to do it with React, of course, because like I think it's the easiest right now to interact with Mina.
Makes sense.
Right,
Awesome. Any other questions? Okay. Oh, Gregor.
I was just curious. So you said that because you dispatch actions, you make it public what everyone voted, right? And that it's not for privacy. That makes sense to me. So did you think about this? Like, did you think? Have you any ideas how to achieve that? Combining privacy-preserving voting and reducer, or is that fundamentally not possible?
Yeah, actually, at first I thought that dispatched events on reducer are private. Then we had a great debate with Boray, and he said that they are not. And we couldn't find the actual documentation of Mina. And then we decided that it's not, because like always think the worst scenario. So we said that like have external on the water. We can of course like encrypt the candidate information to not be able to be readable by others. But I don't know how we will count this type of candidates.
Yeah. Exactly.
Or maybe we can use like hashing the candidates, and somehow when we add the hashes, they give us the number of votes on one candidate. That would be great, actually. That kind of math cryptographic approach would be great, but yeah.
Yeah, we had some iteration at this topic. So this cryptographic scheme is heavily inspired by Semaphore's scheme. So we ran nullifier and we basically mask the voter's identity with that nullifier, and only the user knows that nullifier. So we achieved privacy with that.
Yeah.
not with reducer. So we didn't trust to nullifier to give us privacy.
Okay. You're right. Yeah, I guess it does. So I guess the only thing that destroys privacy is the user sending the transaction, but we will be able to fix that as well.
Yeah, we can relate like transactions. So users can sign TXs, then send to a relayer that can be solved.
Yeah.
Yeah, that's great. Yeah, it works. You're right. Cool. Thanks.